So I'm going to go over the Chapter 9 homework problems. We went over some of these in class, but a lot of people didn't ask about too many of them. So for this one, you're asked to find the impulse when you have a graph of force versus time. So the impulse is simply the summation of the force in time, so it would be an integral, so which is the area of the graph. So I just got the area of this graph, and I got 4 Newton seconds of impulse. For problem 12, it's indicating that you start at negative 10 meters per second. You're given an impulse. You have a final velocity. It's asking what that is for an object with a mass of 0.25 kilograms. So the initial momentum is negative 2.5 kilogram meters per second. The impulse is the area of this graph, which is 500 newtons times 8 milliseconds, or 0.008 seconds. So this plus 4 Newton seconds. So my final impulse is, or my final momentum, plus 1.5 kilogram meters per second. And so if I take that divided by the mass, I get plus 6 meters per second as the rebound velocity. For 15, this is actually a neat problem just because it deals with the change in mass, and we normally deal with a change in velocity. But the change in mass with a constant momentum is causing a change in velocity. So it's rain falling in a train. That even rhymes. Maybe it's in Spain. And so therefore, you have the initial mass and velocity. You have the final velocity, so you can figure out how much of mass of rain falls. That was 500 kilograms. For this, I think we went over it in class. Basically, we need the area of this trapezoid. That's going to equal the impulse. The mass of the ball is 0.06 kilograms. Goes in at 32 meters per second, comes out at 32 meters per second, so we know there's a change in velocity of 64 meters per second. And that total change in momentum would equal F max times 0.04 seconds, because I basically got the area of this trapezoid as F max times 0.004. So that gives me 960 newtons. So I kind of did the piecemeal parts of the area here. Calculus alert, pretty easy, but if force is the derivative of momentum with respect to time, have the momentum formula, take the derivative of it, and I get this is my force. If I have a force, take the antiderivative of that, that would give me momentum. So you have 3 carts, or they're gliders, they're all still. It shows you graphs of the motions at the 200 gram and 300 gram cart. You're asked to find the speed afterwards of the 400 gram cart. So I know that the total momentum at the beginning is 0, so therefore in this isolated system, the momentum at the end has got to be 0. So figure out that the 200 gram cart has a positive momentum based on the slope, which is its velocity multiplied by the mass. And this one has a negative momentum because it's got a negative slope times its mass. And then the third momentum of the third cart is something we could figure out. Divide it by the mass, you get the velocity. So that's negative 0.04 meters per second, or 0.0425 meters per second to the left. This one apparently, I did not have the correct answer on my when I uploaded it, but I do here. A little bit too fat of a line. Let's make it something nice and colorful. Okay, so in this case, you have a 25 meter radius circle. It said 50 meters of diameter, but that's friggin' stupid for this because you're trying to get to the edge from the center. You have 2 skaters at going different speeds. They hit each other, so they produce a net resultant momentum, which is going to be 281.5 kilogram meters per second. Divide that by the mass of the total system, since they are have collided with each other, and so the masses stick together, and I get 2.08 meters per second. Find the angle. I just take the inverse tangent of one side compared to the other, so it's 42 degrees north of west. I think it asked about it being north of west. And so therefore, if I know this distance is 25 meters divided by this velocity, I can get it takes 11.9 seconds to get to the edge of the hockey rink or the ice rink. This one I liked. I just thought it was so weird. It's like, or you could, I guess, try to push this across, or throw it across. Although 5 meters per second is a pretty fast speed to throw it. But shooting a rocket that embeds in there is kind of funny. The key thing here is that this embeds in this, so it's basically going to be a perfectly inelastic collision. But you actually have to work backward to think about it. First of all, in order to need a certain speed across here, you have to find the time to fall. So that's using kinematics. Second thing you need to do is determine the speed you need to get across the river. That's, again, a simple kinematics problem. 30 meters divided by the time we figured out above. That gives us the speed that we need to get across. Finally, to find the speed of that, you need to find the speed of the rocket that is going to launch the package at that speed. But you've got to think about the fact that the rocket is going to be embedded in this package. So it's going to be a perfectly inelastic collision. Mass of the rocket times velocity of the rocket equals the total mass of the system times the final velocity. That's how I get about 28 meters per second. This one is pretty straightforward momentum problem, except it deals with exponents, and I want to get you used to that because it seems like people have been having a little bit of difficulty. So atomic mass units are a very small unit of mass. One atomic mass unit is approximately, let me see here, 1.67 times 10 to the negative 27th kilograms, I think. Oops, I thought I was going to do 62, but it's really 63. So I started doing something that was the wrong problem. Don't worry about it. This is 63. You have three things that are all shot at each other. The best way I do that, this is kind of like a unit vector problem, although I just have it in the x and y direction, no z direction. So this would be like I hats and j hats. But I'm using it for momentum. Notice I keep everything in terms of momentum, and then only at the end figure out velocity. So this gets me a momentum to the east, this gets me a momentum to the south. When I do the trig with these, get the resultant momentum down here using Pythagorean theorem. Then that resultant momentum divided by the total mass of the system gets me the final velocity. To find the angle, inverse tangent again of opposite over adjacent side. I think that's it. So hopefully this is helpful to you, and you get the corrections done when we have our next test. Thanks.